Hi everyone. I want to talk about section 4.8 a little bit more with some examples coming to us from our textbook, and then there will be some opportunity for you guys to do some examples as well. The first four examples are asking us to take these equations and match them up with their graphs. And so if we look at number 3, notice that we have singular multiplicities all the way through. If we have x minus 1 as a factor, then we should have a 0 at 1, and with plus and minus 2, we should have zeros at 1 and plus and minus 2. Also, our n behaviors should tell us that we're going to be going up to the right and down to the left. We are odd, so we're different, and so when we look at this, it seems like we have in A, -2 and +2, +1, our n behaviors are correct. So it feels like we've got f of x for graph A. When we come to B, we have zeros at -2 and at -1. Excuse me, but notice that there's a multiplicity at -2. So when we look, we've got -2 and -1, but we bounce at -2 and we come straight through at -1. So h of x is going to match up with C. When we come to example 5 here, g of x, we have x could equal -1, +1, or -2, and those are all singular roots. -2, -1, +1. So we're looking at g of x for B, and it stands to reason that our example 6 is D. Do we have a multiplicity at +1? We do. Do we also cross at -2? We do. And so we are again looking at f of x. This is number 6. So that's how we can take our functions in factored form and pretty quickly tell how they will graph. We have to zoom in a little bit more and take advantage of our graphing utilities in order to figure out turning points, but that's how we would deal with our zeros. In the second set of directions, I want to deal with numbers 7 and 8. In number 7, we have a 0 at +2, but there's a multiplicity there, and also at -1. So I want to locate where -1 is and +2. Our n behaviors tell us that something that's cubic and positive would tell us that positive, first of all, says to the right we're going up, and if it's cubic, we're going to have opposite n behaviors. So ultimately, I want to be going up to the right, but that's a double root, so I'm going to be bouncing there. I'm also going to be passing through at -1, and that's a singular root, and somewhere along the line, we're going to cross through the y-axis, and if I see -2 times -2 times 1 is 4, I can see where that thing would graph. Feel free to grab some technology if you want to look at that a little bit more carefully, but that's essentially how we would have that. In number 8, in factored form, we have our zeros at -2, but it's squared, so there's a multiplicity of 2. Also at -4, and it also has a multiplicity of 2. And so if we locate this, 1, 2, 3, 4, we have our zeros in both of those positions. When we talk about n behavior, something that is to the 4th degree should have the same n behaviors, and everything here is positive. So to the right, we should be going up because it's in even degree. We both should be going up. There are double roots in both of these, and so we should bounce and bounce again. If you want to check out what 4 times 4 times 2 times 2 equals, we will be up at, looks like 64 for our y-intercept. If it's beneficial, we can see there is our number 7, and there is our number 8. For this third set of directions, I want to take a look at number 21. Can we find all of the zeros of this function? And so I started off by listing all of the possibilities in terms of the numerator coming from what's going to multiply to give us 36, excuse me, and the denominator coming from what multiplies to give us 4. I know that there's some duplications here. For example, if we say that 4 over 2 is the same as 2 over 1, then we don't have to write things twice. And I didn't list out the long, I didn't list them all, but I hope you can understand how we could have 1 over 1 and 1 over 2 and 1 over 4, and 2 over 1 and 2 over 2 and 2 over 4, knocking out some of the multiplicities. So I've cheated a little bit. I worked out this problem beforehand, and I saw that 3 was going to be one of my zeros. It's certainly a good choice. Out of all of these possibilities, any one of these are potential ones. If I chose 5 or 7 or 13, those would be bad guesses because they're not part of our list. 3 happens to be in the list, and let's just look synthetically. If we bring down the 4 and multiply and add, and multiply and add, and multiply again, we wind up with a 0. That's terrific. It tells us that 3, 0 is a point on our graph. They're asking us to find all of the real zeros. When we get to this point where we would multiply to get us to a negative 12, we can come back and realize that 36 and 18 don't need to be checked any longer. We don't have to worry about the 9 or anything else that's going to not multiply to give us 12. And again, if we try any of these or any number in the world with synthetic or long division, what comes out as our remainder will give us a point on our graph. Working ahead of time, I saw that negative 4 was going to work. You just bring down the leading coefficient and multiply. We add, we multiply again. And so negative 4, 0 is a point on our graph. And our final example, or our final 0 here, is actually going to be a fraction. It's going to be 3/4. When we bring down the leading coefficient of 4 and multiply, 3/4 times 4 is just 3. And you can see that that comes out as another 0. So 3/4, 0. Something that is cubic should have 3 zeros. They don't always have to be rational. They don't always have to be real. If either of those possibilities surface, we would have conjugates. So irrational and imaginary roots always come in pairs. These happen to be 3 real rational roots. All of these were possible roots. Only 3 of them actually worked. In number 26, we're asked to graph the function x to the 5th minus 4x cubed plus x squared plus 2. Graph it and then tell where the x-intercepts are, where are the local maximum and minimums, and determine where we are increasing and decreasing. So I've taken the time to plot this out ahead of schedule on Desmos. And first of all, our x-intercepts are where we are going to get 0 for y, because this x-axis is y equals 0. So we have x-intercepts at x can equal negative 2.159, also at +1, and also at 1.747. If you want to list them as points, if you want to have them as ordered pairs with something comma 0, that's great, but those are our zeros. When they ask for a local maximum or a local minimum, we're talking about turning points. Where do we, as we are coming from negative infinity to positive infinity on our graph, we're increasing, increasing, and increasing until we come to a turning point. That turning point is at negative 1.627 comma 10.474. This is just as easy as finding the just what are the coordinates listed here. Our second turning point down at the bottom is at 1.458 comma negative 1.683. And then those are all easy enough to look at. The question that's really more important is, when is the function increasing and decreasing? And so as we read a graph from left to right, we're coming up until we come to a turning point. I know this might be a little bit strange in terms of, we talk about end behaviors where we are down, up, but really we read a graph from left to right. So as we're going in that direction, we're increasing until we start heading down. So we're increasing in terms of x from negative infinity all the way until we get to negative 1.627. Then also, if you notice, we're increasing again after we come past this second turning point. So that was at 1.458, and once we get past that turning point, there's no turning back. We're off towards positive infinity. A union symbol, which looks like a capital U, goes in between there, and it's an OR situation. We are increasing on this graph when we are here or here. We can't be in two places at the same time, but either here or here is where we are increasing. Now, when are we decreasing? In this graph, it is from the turning point, negative 1.627 to 1.458. So as we run through from negative to positive infinity, we're increasing until we come to decreasing, and then we're increasing again. It's a continuous graph. We never have to lift our pencils off the paper when we're doing this, and so it should suggest that that's how we're running. Okay, so it's one thing to just plot something onto Desmos and look at it and just grab numbers off of the graph, off of the illustration, but can you interpret it? Can you understand how we're increasing and decreasing? Notice that the question did not ask, when is the function positive? Positive would be, when are we over the x-axis, above the x-axis, and negative, when are we below the x-axis? That's a different question than when are we increasing or decreasing. Next, in examples 39 through 46, the question is, are we even or are we odd or neither? And remember, when we answer this question, it's not simply is it an even degree or an odd degree. That's been an important question for us. When we look back at number 26 here, this was x to the 5th power. That's an odd degree, but it's not an odd function. This is a weird looking shape. When we come to odd and even functions, you can kind of see the punchline here of what these are going to look like. But we determine it by plugging in negative x wherever we see x and see what comes out. So I'm going to look at number 40 and number 42. Number 40 was g of x equals negative 2x to the 6th plus x squared. If we plug in a negative x and then play this out, we will get a negative x raised to the 6th power becomes positive, so we are left with negative 2x to the 6th. Negative x squared is positive x squared. So the parentheses here are important, order of operations. And so look, we started off with g of x, and now g of negative x equals the same thing. When g of negative x equals g of x, then we are looking at an even function. An even function suggests that there is symmetry over the y-axis. If we are to graph this, there's reflectional symmetry. This is number 40. Do you see how we could fold the left side onto the right side and it would match perfectly? That's an even function. Another good example, oftentimes, of an even function is a parabola, but the parabola needs to be centered on the y-axis. If it's shifted left or right, it will have symmetry over the line of symmetry, but if it's not over the y-axis, then we don't call it even. So please be careful with that language. In number 42, our function was f of x equals x to the 5th plus 3x cubed minus x to the 1st. Again, to check are we even or odd, we plug in a negative x wherever we see x in our original function, and a negative x raised to an odd number is still going to come out as negative. Negative x cubed is negative x cubed times 3, so that's minus 3x cubed. And the opposite of negative x becomes positive x. Our original function was positive x to the 5th, positive 3x cubed, and minus x. All of our signs are reversed. Something we could do here is factor out a negative 1 and be left with the original. So in other words, f of negative x is equal to the opposite of f of x. And if ever we can bring this negative to the outside, then that is odd. And odd suggests that there is symmetry about the origin. Symmetry about the origin means that we should be able to rotate 180 degrees. So that should take you back to a little bit of geometry review. Even, odd. And I just thought maybe it would be a good idea to take a look at number 46 just as a counter example. H of x equals x to the 5th plus 3x to the 4th. What happens if we plug in a negative? We would wind up with negative x to the 5th. Negative x raised to the 4th becomes positive, so it is plus 3x to the 4th. You can see that what was positive becomes negative for our first term, but the positive remains positive for the second. We've lost either an odd or an even nature here, so this is a neither situation. Just two word examples. Number 48, using tools, it says, during a recent period of time, the number of S in thousands of students, so thousands of students enrolled in public schools in a certain country, can be modeled by the equation S equals, and then I'll let you see that thing. It's a long 4-term cubic, where X is time in years. Use a graphing calculator to graph the function for the interval between 0 and 41 years. inclusively and describe how the public school enrollment changes over this period of time. So here's how it graphs. Please feel free to look at section 4.8, look a little bit more carefully at what this function is, and feel free to throw it into a calculator. What you'll see is that from year 0, when we started the test or when the model began, up through the 11.6 year, so for about 11 and a half years, enrollment was increasing and increasing, and then for some reason, between 11.6 and 29.8, there was a decrease. It never got to as low as where we started the test, but then it started to increase again. Now, just so you know, I lopped off the function. The function continues forever, devoid of context. Within the context of the problem, it's only the black portion of this graph. It asks us to stop at 41 years and see, analyze, take a look, describe this thing. Once we get past 41 years, it's entirely possible that the graph no longer follows this cubic model. Maybe it just levels off, maybe it tail spins, maybe it continues to go up, but maybe it goes up at a more gradual rate. But we just want to be able to graph that and then set the window. If you notice, we're up here as high as 40,000, as this line is showing here, and we've only gone from 0 to 41. So I really had to manipulate the window in order to see that. And this question is really, there's no real number crunching to be done. It's asking you, can you use the tool in order to analyze things? And finally, the last example I wanted to give you is a classic algebra question. I don't know if I've ever seen this on an SAT, but I've seen it in SAT prep questions situations frequently. You're going to make a rectangular box, so a bottom and 4 sides. So we're going to have four sides and 1 bottom. And the original piece of cardboard is 20 by 16, but that's flat. That has area. It doesn't have any volume until we get the 3rd dimension, so we've got to fold up the sides. And we're going to do that by cutting X inches off of the both sides. It has to be a square there. It has to be uniform so that when it folds up, the top of the box will be equally high. So when we do this, you know that volume is length times width times height. The first question is, how long should we make our cuts if we're going to try to maximize our volume? So length times width times height. If the full length of the cardboard is 20 inches, but we're going to take X off of both sides, then we should say that the length is 20 minus 2X. If the width was originally 16, but we're going to take X off of both sides, then 16 minus 2X. And when we fold up these sides, there will be a height of X. Please be careful, it's not 2X. We're folding up and only having a height of X. So the first thing after writing this out that I did was I recognized that 20 and 2 are even, so I pulled out a 2, but even better, I think, I pulled out a -2 so that I could rewrite it as X minus 10. I wanted the X to become positive and the 10 to become negative. I did the same thing, 16 minus 2X. I saw I could pull out a 2X, and that, or -2X, and that allowed me to write it as X minus 8, and the X at the end just hung around. Now, pulling out a negative and a negative is equivalent to pulling out a positive, and 2 times 2 is 4. So that's where this 4 came from. It's more traditional to write the X first, and then X minus 8 and X minus 10. So that would suggest that we have zeros at the origin, at +8, and at 10. Also, if we multiplied all of this out, just taking a lazy man's approach here, we have x to the first times x to the first times 4x. We should have a positive 4x cubed plus, and I'm not totally interested in what comes after that. I'm mostly interested in my leading term. The fact that we have a positive leading coefficient tells me that we should be going up. The fact that it's cubic, an odd number, tells me that our end behavior should be different. And so I'm not surprised when I go to my calculator and see that I have zeros at the origin, 8 and 10, and that my end behaviors are operating exactly the way we would like. The question is, how long should we make our cuts? What should our cuts be? In other words, what should X be? Well, what we're trying to do is maximize the volume. And as X is going out along the horizontal axis, our volume is increasing, decreasing, and increasing again. Couple things to consider here. First of all, although the function goes forever, if it doesn't have any context, it doesn't make sense to have a negative cut. It doesn't make sense to have a zero cut. So our domain is going to go from 0 forward. We increase, we decrease. It doesn't make sense to have negative volume. And so I want to lop it off here. You could rightfully ask, well, what about once we get past 10, then the volume starts to go up again? True. In an algebraic, pure algebraic world, I agree with that. But when we come back into the geometry and realize if we try to cut off more than 10 inches, that's not going to work in either of these situations. We can't cut off more than 8 inches. If we cut 8, then we're folding this thing in half, and now we have a height of 8, but a width of 0, so that doesn't work. Our domain has to be between 0 and 8, and in between there, we get this local maximum. So how long should the cut be? We should choose a value of 2.945. Part B, what is the maximum volume? When we choose 2.945, the maximum volume comes out to be 420.11. I said y equals, maybe I should have said v of x. When we plug in 2.945, we will come out with 420. And finally, what are our dimensions? Well, x was 2.945. (20 minus 2 times 2.945 comes out to be 14.11 inches. Our width, 16 minus 2 times 2.945 comes out to 10.11 inches. And finally, our height is at 2.945 inches. When we choose those, we will maximize our volume. There's a worksheet that corresponds to this. The directions are pretty much the same for most of them. Thank you for watching. Please ask if you have any questions.